Question 2. Question 2 is about everybody's favourite, the motor effect. So we can see here that we've got this diagram, this classic diagram with a motor effect in action. And it says when the switch is closed, there is a 2 amp current through the wire. The wire experiences a force and moves. So use the correct word from the box to complete the sentence. The demonstration shows I just told you, the motor effect. State 2 changes that the teacher could make to the demonstration, each of which that would increase the force on the wire. The teacher does not touch the wire. Okay, so how do we make the force on the wire bigger? Now, I think it's probably a good time here to actually explain the motor effect a little bit, because, it's come up early on this predictor paper, but if it's on your actual paper and it comes a bit later on, you might be asked to explain what's happening. So, remember, we've got a switch here. If we close the switch, then we will, close, switch, causes the current in the wire. Okay, so that's step 1 if you're trying to explain what's going on. Closing the switch causes the current in the wire. Alright, so that current is going to flow from positive to negative. And as you can see, it flows through that magnetic field of the permanent magnet there. The second thing is when you have a current flowing through a wire, you will get a magnetic field in concentric circles around the wire. So you could say that a magnetic field is induced, produced around the wire. Yep, because whenever current flows through a wire, a magnetic field is produced. Now, when that wire is placed within a magnetic field, so we can see that happening here, you have to think about what happens when 2 magnets are put together. So if you have 2 magnets on a table and you put them close enough so that the magnetic fields start to interact with each other, then they'll experience a force. They'll either be attracted or repelled, depending on which way around they are. And exactly the same thing has happened here, because basically the wire with the current flowing through it is now a magnet, and the permanent magnet also has a magnetic field. So the third point when explaining the motor effect is that the magnetic field of the wire and permanent magnet interact. Okay, and the fourth thing, as I've just said, when they interact, there's a force on the wire which will cause the wire to move. So a force is applied to the wire and it moves. So in this case, you've just got a wire at 90 degrees cutting through that magnetic field. So the magnetic field lines will be doing that. I'll zoom that in a little bit so you can see the magnetic field lines are doing that. The wire goes through it, so it's at 90 degrees. And it'll just cause the wire to move. If you coiled that wire into a solenoid, then it would cause the, not into a solenoid, sorry, but into a coil, then it would cause the wire to turn, and that's when you got the motor of that constantly rotating wire. But in this case, a single wire just going straight through is just going to cause the wire to move. So now that we know a little bit about the motor effect, we should be able to answer these questions. So 2 changes that could make the force on the wire increase without touching it. Well, we could increase the current because that would increase the strength of the magnetic field around the wire. So increase the current in the wire. And the other thing we can do is we can increase the strength of the magnetic field of this permanent magnet. Again, it's just like putting 2 magnets together. The stronger the magnets, the more force they'll exert on each other. So increase the strength of the permanent magnet. Okay. State one change that the teacher could make to the demonstration to change the direction of the force on the wire. So this is to do with Fleming's left-hand rule again. Everybody's favourite. So remember, in Fleming's left-hand rule, we use our fingers at right angles to each other. And we use 3 fingers. We use F, B, so that's our first finger and index finger. And then we use the third finger as the current, and it's FBI. And they're all at right angles to each other, like that. But I'm trying to draw in 2 dimensions, so it doesn't look great. So if we want to change the direction of the force, then we have to change the direction of B, the magnetic field flux density, so that basically the direction that the magnetic field is flowing, and they always flow north to south, so we just switch the magnet around. Or we change the direction that the current is flowing. Now I should be able to demonstrate that with a little bit of something I can do on the iPad. So if I just try and do this, let's see if I can do it. If I resize, good, it gives me an option to rotate. So you can see at the moment that the force is currently pointing to the top, and the current is pointing towards us, and the magnetic field is pointing to the right. If I flip it around so that the current is now, the force is downwards, you can see that the magnetic field is now pointing to the left, and the current is now pointing away from us. So by reversing the current or the magnetic field, we can reverse the direction of the force. So state one change, let's just say reverse, need a pen, the direction of the, we can pick either, the current. Right, that's dead easy to do. We just switch the wires around on the power pack, so we're flowing making the current go in the opposite direction. When the switch is closed, the teacher changes the position of the wire so that the force on the wire is 0. What is the position of the wire? So I mentioned it earlier, we're talking about the motor effect, and I'll zoom into this section here. The wire has to go through at 90 degrees in order to experience a force, because it must cut through the field lines. If it goes through at 45 degrees, it is still going to cut through the field lines, so there still will be a force, it just won't be as powerful. But if it is running in parallel with those lines, there will be no force. So in order to have no force, the wire must be parallel to the direction of the magnetic field. Okay, end of question 2.